that okay? Or is that too much? Because I mean,
Is
I
it
just want this, the thing is, this one is kind of,
Is it just that projector? Or
I think it's just this projector.
Maybe we can use
If
it-
you're okay with it being like this, I can keep it like that, but most of the people are on this side and then. once you-
Well, and it's solution, we have people to move to this side.
Then that would have to be the other issue.
I think it's a lot easier than replacing an entire.
Okay, you guys wanna do that?
Yeah,
Because I don't know why this is.
yeah, just why we can,
I'm sorry.
no, don't worry about it. I mean, you know, these things happen. And, I mean, we can maybe like place it between talks or something.
Yeah, that's fine. Just wanna know like this, and then keep searching. Yeah, it's a projector itself. So, yeah,
It's not a multi-cable.
no, it's the projector, it's probably the light on the projector, because see that.
Right.
Since your next break.
So we have a talk, each talk is 12 minutes, then we have a 3-minute break between talks. And this is the last session of the day. So, yeah, like, the best time to do would be between talks, or it isn't really worth it replacing it afterward because there's no time pressure.
Gotcha,
Yeah.
okay.
But, I mean, you can replace it obviously, but it's not like you have to do it really fast.
There's somebody coming with the other one,
Okay, yeah, we think.
if you guys wanna continue and then it comes in and we'll probably replace it.
Yeah,
Is
that
that-
sounds good. Yeah, maybe like, yeah, we'll wait until the first speaker is done with their talk.
Okay, gotcha,
Because I mean, it might be
I'll be
distracting.
I'll be out there if you want.
I mean, you can listen if you want.
It's like,
It's, automata processing. We're gonna start on time.
Testing? Okay. All right, everybody, welcome to Processing in Memory 2. We have 4 great talks for you all. The first talk will be given by Kaiyuan. He'll be telling us a bit about his work on automata processing for PIM hardware. Kaiyuan is an associate professor of electrical and computer engineering at Rice University. He received his BS in electronic engineering from Tsinghua University, China in 2012, and his PhD in EE from University of Michigan, Ann Arbor in 2017. His research interests include low-power integrated circuits and system design for secure and intelligent microsystems, bioelectronics, hardware security, and mixed signal computing. And I will go ahead and let him share his work with us all.
Thank you for the introduction. So regular expression matching, which you probably have done in operating system or in PDF, you search something, right? It actually has broader applications across text processing, protein searching, network security, like network monitoring, and also a lot of data mining applications. When you want to match against a large and complex pattern library, you need to consider how to implement that efficiently. And the classical ways of implementing regular expression is to convert them into finite automata, or in other words, a finite state machine. There are 2 commonly used type of finite automata, deterministic and non-deterministic. The non-deterministic or NFA, it's exponentially more succinct than DFA. So most designs are targeting efficient implementation of NFA. And there are certain very commonly used constructs in regular expressions, such as concatenation, alternation, and cleaning star. So we need to support all of this. In a nutshell, what the automata do is you convert from a regular expression like this into something that is like a state machine. And then you use specialized hardware or just a CPU to implement this. At any given input, you do a transition. If it matches, you do the transition. If it doesn't match, you don't do the transition. You go back to the initial state, right? And in this way, as long as at any point you reach the final state, the reporting state, it indicates that you have got a match. Okay. And of course, the most commonly used platform for running these things are CPU and GPUs. But as you scale up the number of patterns you want to match and the complexity of the regular expressions you want to match, the irregular and high bandwidth memory access becomes a bottleneck in these general purpose platforms. There are certain very specific optimization techniques in software that could accelerate them, such as Intel Hyperscan, and also some recently proposed GPU acceleration work. But still, they could not circumvent the fundamental limitations in this so-called memory wall in this general purpose computing system. FPGA, it's a possible solution because it offers very high hardware level parallelism. However, for this NFA operation, because the state transitions can be totally random, arbitrary, and very complex, the routing between the lookup tables in the FPGA quickly becomes a bottleneck. So whenever you try to map a large problem into an FPGA, it's always stuck there during the synthesis because it cannot do the routing properly. And then in the last decade, there has been some growing interest in building ASIC for automata processing. Started from the pioneering work by Micron. It's called Automata Processor. It used DRAM computing to do this pattern matching, and then followed up by some more work that use different type of SRAM or content addressable memories. And they show great promise for high parallelism and high efficiency. However, what we find is that a lot of the regex in real-world benchmarks, they heavily relies on bounded repetition operations, which simply means you see a certain pattern for a certain number of times. It also could be a range of time, and this repetition becomes more complex when they are becoming ambiguous counting, which means you have to remember the history of all the matching, all the things that get into this repetition. And that require very high memory cost. And out of all the benchmarks that we look at, although only 20% of the regex have bounded repetition, but if you directly compile them to NFAs, they account for 85% of all the NFA states. Okay, but as I mentioned, all the existing work, both the software level optimization or the hardware level acceleration, they do not consider this bounded repetition. So they implement everything with the vanilla NFA model. So here I will quickly go over the possible solutions for supporting bounded repetition. The first and the most common, most straightforward solution is to enroll them into a basic NFA. So for example, here, if you have this counting of sigma means any character, sigma A for 3 times, you can enroll it into a chain of state machine, right? But as you can see, this will exponentially grow the size of your NFA and require more memory and more energy to operate. And here I show what is the most state-of-the-art in-memory AP style processor for running NFA. So it basically consists of 2 memory banks. So the first green bank is for matching the input pattern inside memory. And then this crossbar is for routing. So the transitions between the states are encoded in this crossbar. And both can be implemented with SRAM. So here I will quickly go through this simple example. So for example, your input comes here. It's A, so you match ST1. And then ST1 goes through this transition table. It will activate ST2. And next, if you see a sigma or a B, it can match anything. Then ST2 will be activated. It will then activate ST3 and also ST1 because ST1 is always on state. It is at the beginning of the pattern. And then next, I see another A. So ST3 will be activated, and that will activate ST4 and 1 and 2. And similarly, you can keep updating the active status of your states until you reach the final state. And this indicates you have a matching of this pattern. Okay, so that's the basics of how it works. And next, let's go to how to better support the bounded repetition. So our collaborator, Ghostas, their group has recently proposed a automata model called a non-deterministic bit vector automata. It's basically using bit vector to quickly support this running of the automata. Okay, so they use a bit vector to remember the counting status, and that will require less memory than actually expanding and unrolling the states. However, directly implementing this model on hardware will require something shown on the right. Okay, we have to replace the crossbar routing array by a PE array. And each PE need to support different type of operations. And this require exponentially, quadratically scaling area and power consumption. So the solution we are proposing here is we enforce action homogeneity on the NBVA, which means for every destination state, we require all the actions going into this state to have the same action. And this is achieved through a wonderful collaboration between a hardware design group and a PL group. So we have a transformation method, a compiler for going from NBVA to HNBVA. And then we have a custom-made, very efficient and compact bit vector module that is an add-on block to an AP-style processor. And then we have an end-to-end compiler and simulation framework. So here is the transformation from NBVA to HNBVA. We essentially convert all the transitions that have take different actions into one state into different activations by repeating and duplicating the states. And then here is our BVAP circuit. This is a custom designed circuit block. It supports 48 bit vectors. And then it have its own routing crossbar. And it is compatible with any AP-style automata processor. It supports these actions. As we have established in the paper, this set of actions are sufficient to support all possible use cases. And this hardware has a mini instruction set to support the different 6 different actions. And then we have a special memory allocation for the bit vector. It's basically every bit vector here, it has a 8x8 SRAM that stores the bit vector value. We do this serpentine style of data allocation to simplify the shift operations. And then the actual operation of this bit vector module is done in 2 steps. So first step, you just read from this bit vector memory. And then second step, you will read the bit vector, do some operation at the read port, and then go through the transition table to send this BV value to the destination state. And here is the timing of this bit vector processing. We do a optimization that's called semi-parallel as a result of the trade-off between parallelism and area. So we end up having, for each word, we have to do it in 8 cycles. And here we show the timing for the copy operation and the shift operation of the bit vectors. And then this crossbar router is supporting a transition from one bit vector state to any other bit vector state. And here we have some circuit technique. It's a compact 4-port cross-point router. It's essentially a 6T SRAM cell plus 4 ports. As a circuit group, we actually implement this in layout in 28 nanometer. And we show that the maximum number of ports you can support is 4. Otherwise, the area will grow a lot. So we end up with this 4-port design. It provides 30% area savings compared to having 4 independent 8T SRAM cells. This is the overall architecture of the BVAP. It is built on top of our previous work, Kama, which is only support vanilla NFA. And then here, each BVAP tile supports 256 STs and 48 bit vector STs. And 16 of these tiles form one array with inter-tile global routing to support more complex and larger NFAs. And then 4 BVAP arrays form one BVAP bank, and they share all the I/O buffers that will get the input and the pattern from DRAM. Here is the timing. So there are 2 timings we designed for this BVAP structure. The first one is because the BV processing takes more time than the normal state transition. So the first design we have is a time event-driven design. So whenever you see a bit vector operation, the need to do a BV operation, we will stall the state matching to do this. So this overall gives a higher throughput. However, it will not support constant input throughput streaming. To support constant continuous input streaming, we have this second operation mode. In this mode, we make the state matching and state transition taking longer time so that they can hide all the time to do the BVA processing. And in this way, we can lower the supply voltage for state matching and state transition, so they will take less power. This is our evaluation setup. As I mentioned, we have a complete circuit implementation of the BVM, and all the custom circuit modules are designed and characterized with TSMC28 PDK. We also have a custom cycle accurate simulator for the full system function verification and a regex to hardware compiler. Our evaluation setup, we use 7 data sets from real-world benchmarks. So this is a micro benchmark. For a simple case, we show how much improvement we get by adding this BVAP over comma. And then over real-world benchmarks, all the state-of-art designs, we can achieve considerable improvements in terms of energy efficiency, area efficiency, and figure of merit. So overall, we present BVAP through a hardware-software co-design, and includes a novel method to transform NBVA to AHNBVA, and the circuit design of the BVM and the complete architecture. And we'd like to thank NSF for supporting this work.
All right, please line up if you have any questions. We maybe have, we can take a question or 2 before the next talk. And if the next speaker could please come up and start setting up. Okay, I mean, I have a question. So for the match and for the state matching and the state transition, is the analog behavior of the crossbar array used, or is it?
It's actually a digital behavior,
Okay.
but it's done inside the memory.
Okay, so there's a digital logic inside of the memory, and so are there any error rates associated with it, or is it no?
We try to make it error-free,
I see.
but it is accessing multiple word lengths. So
I
you can
see.
say that's an analog behavior,
Yeah.
but it is not an analog readout.
I see.
So it's different from the analog PIM, which always have errors.
Yeah.
In our case, the result is deterministic.
I see. So the chance, you don't have like there isn't really like a chance that you're going to have a spurious match.
No.
I see. And the second question I have is, well, I'm assuming you can always go from NBVA to AHNBVA. What are the overheads associated with the transformation? I'm assuming you have to insert auxiliary states.
Yes. So I think we have characterized that in the paper,
Okay.
but I don't remember the number.
All right, I'll check out the paper. Thank you.
There is certain overhead for that.
Excellent. Thanks for answering my questions. All right, our next speaker is Minseok So. He is from Seoul National University. He's a 3rd-year PhD student. Minseok is broadly interested in AI accelerator design and will be telling us about his work on performing neural processing using processing and memory architectures. He is currently looking for an industry position.
Thank you for the introduction. Hi, I'm Minseok So from Seoul National University. Today, I'm going to present IANUS, Integrated Accelerator based on NPU and PIM Unified Memory System for end-to-end inference of large language models. This work was done in collaboration with Seoul National University, KAIST, SK Hynix, and SAPEON. Recently, transformer-based large language models are opening a new mainstream in AI services. With growing demands of these services, accelerating end-to-end inference of large language model is essential. The end-to-end LLM inference consists of two stages, input summarization stage and output generation stage. The input summarization stage processes multiple input tokens, while the generation stage generates a new token based on a single token produced right before this stage. Each stage exhibits unique computational characteristics based on fully connected layers, which account for many overflows in LLM. With the matrix input, the summarization stage is compute intensive, with FT layers representing matrix-matrix multiplication. In contrast, the generation stage is memory intensive with both matrix vector multiplication. In addition to FC layers, LLM includes attention that has many data manipulation operations. Also, LLM includes vector operation that features parallel arithmetic operations. To accelerate this operation, many hardware accelerators have been introduced. For GEM operation, GPU and NPU are effective. Meanwhile, FPGA-based appliance named DFX and processing in memory excel in GEM-B operation. Also, specialized accelerators are designed to optimize attention and vector operation. However, these accelerators only accelerate certain operation or stage of LLM, not the end-to-end inference. To accelerate end-to-end inference of LLM, we come up with domain-specific system architecture that integrates commercial domain-specific accelerator with commercial domain-specific memory. Specifically, we use data center targeted SAPEON's NPU and SK Hynix AIM, which is PIM solution based on commodity DRAM. Now let's see how previous PIM systems have integrated PIM into their architectures. Previous PIM system uses PIM as an accelerator and employed the partition memory system, where host NPU in our work has own dedicated memory, and PIM also has separate dedicated memory. This system maximizes parallelism between NPU and PIM, but it leads to inefficient memory usage due to shared data duplication across both memories. In LLM, since shared data account for about 90% of total model parameters, the memory capacity overhead from data duplication is problematic. To address this, we propose integrated accelerator based on NPU and PIM unified memory system, where PIM memory is used for main memory of both NPU and PIM compute unit. This system improves memory efficiency by eliminating the need for data duplication. We call this system IANUS, since it shares similarities with Roman God IANUS representing dualities. Now let's delve into the architecture. The IANUS consists of one NPU and 4 PIM chips. Each core in NPU includes the matrix unit, vector unit, scratchpad, and DMA. The matrix unit executes GEM operation, and the vector unit executes vector operation. We enable data manipulation in attention through coordination of scratchpad and DMA. These operations are executed based on commands which are organized by the command scheduler. For the PIM architecture, IANUS uses PIM with near bank processing that places processing unit close to each memory bank. This design allows for parallel execution across processing unit, therefore accelerating GEM-B operation with enlarged bandwidth. However, just integrating NPU with PIM introduces inefficiencies by 2 challenges. First, the significant overhead in command scheduler is caused by differences in compute granularity. For example, this application with 3 operations require only 4 commands on the NPU alone. However, using PIM to accelerate GEM-B operation results in a large number of commands, since PIM command has small compute granularity for compatibility with commodity DRAM. Therefore, coarse-grained command is required for PIM. The second challenge is limited parallelism due to sharing same PIM memory. When PIM computation is active, NPU's DMA has to be postponed, leading to underutilization of NPU. Therefore, effective workload mapping and scheduling is essential for use of both compute capabilities. To address the challenge from granularity mismatch, we propose macro PIM command. This macro PIM command consists of multiple PIM commands, allowing command scheduler to manage PIM commands as a single entity. However, since PIM doesn't support macro PIM command, we propose PIM control unit that decodes macro PIM command to PIM command and sends decoded PIM command to PIM for computation. Also, we employ PIM memory controller to support both DRAM command and PIM command. To address the challenge from limited parallelism, we propose PIM assess scheduling that maximizes parallelism through workload mapping and scheduling. Here is a simple application example showing the effectiveness of PIM assess scheduling. Each node represents an operation cycle and optimized mapping execution unit. And each edge indicates the dependency between operations. After the first vector operation, there are two options, PIM computation and NPU's DMA. Instead of executing PIM computation first, which takes 9 cycles, our method schedules NPU's DMA first, improving performance with parallel execution of PIM and the matrix unit. Now let's see complex application for the mapping scenario. With scheduling previously described, the total cycle reaches 15 cycles. Despite using optimized mapping for each operation, there are inefficiencies. Notably, the matrix unit is underutilized. To address this, our method maps this GenB operation to the matrix unit. Although GenB operation takes longer cycle in the matrix unit, the overall cycle decreases. As a result, PIM assess scheduling effectively overcomes the challenge from unified memory system. To evaluate the IANUS, we developed cycle accuracy simulator based on simulators of commercial NPU and commercial PIM. For effectiveness in various LLM services, we use GPT-2 with compute-intensive inference and memory-intensive inference scenario. We evaluated 4 accelerators. The table shows specification of each accelerator. For compute-bound accelerators, we use A100 GPU and NPU. IANUS shares identical specification with NPU, but using PIM instead of standard GDDR6 memory. We also evaluated DFX, which achieved the state-of-the-art performance in memory-intensive inferences of LLM. We compared the end-to-end inference latency of GPT-2 across 4 different accelerators. We evaluated 5 scenarios bearing the number of output tokens. As the number of output token increases, the inference becomes memory-intensive with more generation stages. In scenario with only a summarization stage, GPU and NPU and IANUS exhibit low latency. However, with more generation stages, GPU and NPU experience significant latency increases, while DFX achieves minor increase. Thanks to PIM's capabilities, IANUS outperformed DFX by 1.8 times in generation stages. Please note that this graph is in log scale. Also, PIM assess scheduling contributes to this improvement by achieving 1.3 times speed up compared to naive scheduling. With effective architecture and scheduling, IANUS achieves the best average performance in end-to-end LLM inference. In summary, IANUS is heterogeneous architecture combining a commercial NPU with commercial PIM. Also, it is an accelerator for the end-to-end LLM inference through accelerating all diverse compute characteristics in LLM. Also, it achieves efficient memory uses by employing unified memory system. We also propose PIM assess scheduling that effectively maximizes parallelism between NPU and PIM through workload mapping and scheduling. Thank you for paying attention to my talk.
If you have any questions, we have a few minutes, so.
and also the next speaker could get set up too. Great. Questions, anybody? None? Okay, I have a question. So I mean, what is the programming interface like for working with this system?
Actually, the programming interface, we support all programming interface such as C or Python. Actually, one of the problem is backend. So we use the backend something similar like TPU, Google's TPU.
I see.
And for the PIM, we use library based. So we just call in some API to program it.
I see. So when you're programming, when you're implementing your program, you have to manually specify what you want to be executed on the PIM. That's not decided by the scheduler.
Yes, right.
I see. So there's like there's basically a special instructions.
Yes,
it passed through.
Yes, right.
I see.
Yeah.
Is there any hope to automate?
Yeah, we
have to
think about that as a future work.
I see.
Yeah.
And as far as data movement, like, do you have to manually figure out where you want your data?
Oh, no, we don't have to. We just specify something for the PIM, then it automatically offloads the data to PIM from the NPU.
I see.
Yeah.
Okay, so the data movement is taken care of.
Yeah.
Thank you. Other questions? Okay, so if you don't mind getting prepared, Andre. And thank you.
Thank you.
All right, so we actually need to wait 2 minutes.
Okay.
In case anybody is coordinating their sprint to the Fairview conference room, you know. Yeah, I'm not sure if they replaced the projector. I wasn't paying attention, but.
No, you can set it, but I don't think it's replaced.
Okay, has it been bothering anybody? No. Yeah, I have to admit, my field of view isn't that wide. All right, we can probably get started. See you. All right, next up we have Andre Lopez. He is a second-year PhD student from the University of Lisbon. He is broadly interested in distributed systems, transactional memory, and processing in memory. And today he'll tell us about transactional memory for PIM systems.
Thank you for the introduction. So my name is Andre Lopes. I'm from the University of Lisbon and in SKD, and today I'm going to present our work where we introduce the first software transactional memory implementation for processing in memory devices. Modern workloads are becoming increasingly data intensive, requiring to process large amounts of data, often with random access patterns. Due to this movement, these workloads often suffer from the data movement bottleneck problem, where the overall performance of an application is degraded due to the sheer amount of data that is to be moved between memory and the CPU. Recently, processing in memory has emerged as a technology that aims to take care of this problem. Processing in memory, as the name suggests, departs from the traditional processing paradigm by performing computation directly in memory. The UP-PIM hardware is one of the first publicly available processing in memory devices that achieves the goal of performing computation closer to memory by equipping memory modules with very simple processors. These very simple processors are called data processing units or DPUs and have two key characteristics. First, each DPU has 24 hardware threads which can communicate via shared memory. And second, there is no direct communication between DPUs. If communication is required, it has to be mediated via the CPU, which is costly and thus undesirable. In total, the UP-PIM system has a total of 2,560 DPUs, which can operate concurrently and independently. So, given the fact that this device offers parallelism, this raises a problem of having to synchronize concurrent access to shared memory. Traditionally, Traditionally, this has been done by using lock-based schemes. However, lock-based schemes are hard to use and error-prone. So, transactional memory has emerged as a simpler alternative, whereby leveraging the concept of transactions, programmers only have to identify which code sections have to be executed atomically and in isolation, while delegating to a transactional memory system how atomicity is implemented. Despite transactional memory being simpler than lock-based schemes, it can still be as efficient through the use of speculative concurrency control schemes or through the use of hardware mechanisms. In this work, we investigate for the first time in the literature how to implement software transactional memory in processing in memory devices. Specifically, we introduce PIM-STM, which is a library that includes a set of STM implementations for the PIM device. The goal of PIM-STM is to simplify the life of programmers that want to leverage the full potential that is offered by these emerging hardware architectures that require the use of parallelism to synchronize concurrent access to shared memory. PIM-STM is a library that exposes a standard STM API where programmers can manage the lifecycle of applications and can issue read and write requests to local shared memory. Since we designed PIM-STM for the PIM system, we needed to keep in mind 4 key characteristics of this hardware. First, there is no direct communication between DPUs. If this communication is required, it has to be mediated by the CPU. Second, communication and computation cannot be overlaps, which precludes the use of speculative techniques from the distributed transactional memory literature, where the communication and computation are overlaps in order to hide internode communication latency. Third, the PIM device offers 2 memory tiers, WRAM, which is smaller but faster, and MRAM, which is bigger but slower. Finally, the PIM hardware only offers atomic operations with very limited semantics, which raise some difficulties when trying to implement transactional memory. So, due to these characteristics, we made a decision not to support distributed transactions in PIM-STM and restrict these transactions to operate on the data that is hosted in a single DPU. This represents a very common trade-off between the generality of programming of these abstractions and the performance that they can actually achieve in practice. This choice is key to ensure the maximum performance by applications that use PIM-STM and avoid the very high overheads that would be incurred by using distributed transactions in the PIM device. So while designing PIM-STM, we strive to include in it a set of implementations that would allow us to explore exhaustively the STM design space. Given that we target programs that are coded using the C programming language, we focus on single version and word-based transactional memory devices, which leaves us with 4 main design choices. Metadata granularity, which is the level at which conflicts are detected. Read visibility, which determines whether reads are visible to concurrent transactions. Lock timing, which determines the time in which locks are acquired. Locks not in the common sense, but in the sense of locks locks in the TM system. And write policy, which determines when writes are made available to the exterior. Note that in the slide we include the taxonomy of the STM implementations that we include in PIM-STM, and here we have 2 well-known STM implementations from the literature, NOREC and PIM-STM, and we also include a novel implementation, which we've called visible reads, and is based on read-write locks. Using dashed lines in this taxonomy, we highlighted the implementations that are either incompatible because they would break correctness or are undesirable because they would impose prohibitive performance overheads. Since PIM-STM was designed for the PIM device, we provide key characteristics or key functionality targeted at specific hardware features of the PIM device. Since the PIM device has 2 memory tiers, WRAM and MRAM, we allow programmers the choice of where to keep their transactional metadata. Programmers, depending on their specific use case, may wish to keep application data in WRAM, which is faster, and to do so, we allow them to offload the transactional metadata to MRAM. The inverse case is also true. If programmers want to keep the transactional metadata in WRAM in order for it to be accessed faster, they can offload the application data to MRAM. Second, normally when implementing transactional memory, the use of compare and swap operations is required. However, the PIM device does not support natively this operation. So using the only atomic operation that is provided in the PIM device, where a single bit in an atomic register is acquired, we built functionality that is similar to compare and swap and allowed us to implement the transactional memory. I'm not going to explain this in more detail here, but if you have any questions or doubts, you can look at the paper. In our evaluation, we strive to answer two main questions. First, which STM designs work best for different workloads? And second, which performance and energy gains can be achieved while using PIM-STM to accelerate applications that were originally designed for CPU-based systems? To answer the first question, we use 4 workloads running within a single DPU. This allowed us to assess the performance and scalability of the STM implementations included in PIM-STM as the number of threads within each DPU or within one DPU increased. To do this, we use 4 benchmarks: 2 concurrent data structure benchmarks, array bench, which simulates transferring money between bank accounts, and linked lists that where a bunch of insert, remove, and find operations are performed on a linked list. Then we use 2 more realistic workloads, K-means, which is a clustering algorithm, and labyrinth, which is a circuit routing application. Due to time constraints, I won't be able to present all of the takeaways that we have in the paper. However, if you have more details, you can look at the paper. So in the graph on the slide, we can see the average performance of the STM implementations that we include in PIM-STM across all of the workloads that we tested. So here in these graphs, lower is better. It means that an STM implementation performs better. As we can see, NOREC on average is the best performing STM implementation across all of the workloads that we tested. However, on the graph on the right, as we can see on the x-axis, the number of threads within each CPU and the performance in the form of throughput that is achievable by each of the TM implementations. In the black line, we see that NOREC in certain scenarios can still underperform all of the other implementations, which leads to the conclusion that there is no one-size-fits-all solution regarding STM for PIM. The best STM implementation for PIM is dependent on the workload in question. Second, to answer the second question, which speed up and energy gains can be achieved by using PIM-STM to accelerate applications that were originally designed to be executed in a CPU, we use two benchmarks from before, but now using all of the 2,560 DPUs that are offered by the PIM device. Specifically, we use labyrinths where we have a different instance of labyrinth running in each of the DPUs, and we use k-means, which we've adapted in order to be able to partition these workloads across all of the DPUs. The graph on the slide shows us the performance gains that PIM-STM was able to achieve over a reference CPU system running the exact same workloads. As we can see, PIM-STM is able to outperform in terms of speed up the CPU system in all of the scenarios tested, and is able to obtain energy gains in all but one of the scenarios that we evaluated. This led to the conclusion that PIM-STM has an excellent performance potential. However, there is still some room for improving on the energy efficiency fronts. In conclusion, in this work, we presented the first STM implementation for processing in memory devices. We performed an exhaustive study on the trade-offs or on the key takeaways on the key design choices on STM from PIM devices, and we provided some guidelines for programmers that in the future wish to use transactional memory for processing in memory devices. And finally, we performed a comparison between PIM-STM and a CPU-based system, where we were able to obtain very good speedups, and we were also able to obtain gains regarding energy efficiency, despite these gains being more modest. Thank you, and I'm willing to answer any question.
Yatin Manerkar, University of Michigan. Thank you for the talk. Can you explain briefly how your scheme enforces conflict detection and rollback of transactions?
So how the transactional memory implementation enforces those properties that you mentioned.
Right, but you're doing it for PIM, so it's a different underlying
Yeah.
implementation. So you'll have to do something different, right?
Yeah, so we have several implementations. I can briefly explain NOREC, which is one of the implementations that we include. So NOREC is, as the name suggests, is an implementation that is specifically designed for having low parallelism, so low transactions executing concurrently. The main key design of this implementation is that they don't have ownership records. So they cannot finally track conflicts between data positions or data addresses. What they do is they use a global clock, where the global clock is increased every time a transaction commits. So what happens? When a transaction commits, the clock is increased, and transactions that are currently executing, they know, okay, a transaction committed, so my data might have been invalidated, right? Because this transaction wrote some of values that I might have written. So what do I have to do? I have to go to the position that I previously read, and I have to validate them again. I have to see, okay, did the value that I saw before is still the value that is in memory? If it is, I can continue executing. If no, I have to roll back and abort the transaction. Yeah.
Do you think that that sort of heavy-handedness is potentially causing the increased higher energy usage that you're seeing?
I wouldn't say so. We think that the higher, or the less good or less satisfactory results in terms of speed up are kind of due to the specific hardware. In private conversations with the developers of this system, they have told us that this is a problem that they have also identified, and they plan to rectify in next versions of this device.
Thank you.
Thank you for your question.
Other questions? And also, I guess while we're discussing, maybe the next speaker can come get set up. That'd be great. It'd be great if the next speaker. Yeah. So maybe I missed it. So what was the cause of the increased energy consumption? He alluded, I think he was asking about whether there was a certain phenomenon that was causing it, but I missed the actual.
No, I would say that it's mainly because of the consumption of the hardware, which is kind of high. Sorry. Yeah, these less satisfactory speedups or energy gains are mainly due to the hardware, to the energy consumption of the hardware. It's the first version of the hardware, so they were not focusing on energy efficiency, which then in our results are not great.
I see. Did you try disabling parts of your transactional memory system to see the energy? Does that make sense? Like an ablation study kind?
Not really. So we analyzed each part of the transactional memory. So the read phase of the transaction, the write phase, and so
Okay,
on.
so you figured out you like built it, you did a breakdown.
Yeah, but it really not gets a specific energy data for those breakdowns. We just analyze it from the standpoint of performance.
I see. And did you collect like a power trace?
The hardware is not supported. So
Got it, okay.
the energy measurements are like very rough. We know the TDP of the system,
Yep.
and we know which time our application took to execute, so we just multiply it.
I see.
Yeah, so yeah, that's the only way to do it.
Yeah, okay, got it. Thanks. All right, and now I'll introduce the next speaker.
All right, our final speaker for this session is Xixin. She is a second-year student at Zhao Chinese Academy of Sciences. Her broad research area involves compute and memory systems and architectural design space exploration. And she'll be telling us about her compilation framework for compute and memory accelerators.
Hello, everyone. I'm Shixin Zhao, and I'm from the Institute of Computing Technology. Today, I'm gonna introduce our work, SIM-MLC, a multi-level compilation stack for computing in memory accelerators. First is our background. The computing in memory architecture executes in-suit computation in the memory, featuring advantages such as high parallelism and no computational overhead. In recent years, researchers have proposed many SIM chips showing their superiority. SIM diversity mainly includes the diversity of architecture hierarchy, scheduling granularity, and instruction set architecture. These factors all affect the SIM behavior. For example, different memory devices such as SRAM and pre-run or have different read and writes overhead. Meanwhile, different program interfaces need customized compilation optimization. However, with the gradual complexity and diversity of applications, such as well as the increasing diversity of different same chip architectures introduced by academia and industry, providing a uniform midware compilation tools to adopt the changes from the both end become important for reducing redundant work and helping hardware designer quickly demonstrate application potentials. However, these mental dimension variations pose two main challenges in designing a general compilation stack. The first one is how to enhance the generality of the compiler, and the other is how to generate the optimal mapping and scheduling for different SIM that expose different operation levels. To overcome this challenge, we propose SIM MLC, a multi-level compilation framework. We first designed uniform abstractions from diverse hardware, including matter-tail hardware abstraction and computation modes. Furthermore, to reduce the huge scheduling space, we propose the multi-level scheduling optimization, progressively optimizing operator mapping and scheduling. Since the same chips often feature different instruction set architectures, using machine code to represent the computation result may lead to compatibility issues. To address this problem, we introduce the meta operators, which can be easily converted to specialize the machine code according to users' requirements. And for the hardware architecture abstraction, we model the same accelerator as a hierarchical architecture, which contains three tiers from top to bottom: chip, core, and crossbar. Each tier has their parameters that contribute to the same feature. Users can define their own chips through setting their corresponding parameters, as the example shows. Similar architecture may vary in their support for different levels of same operation granularity. To chapter this diversity and facilitate optimization, we also introduce a three-level computation abstraction: core model, crossbar model, and word-line model. Users can define their chips' program interfaces by selecting the corresponding computation mode. Building upon hardware abstraction, we introduce the meta operators to represent the computation result in a clear and reasonable manner. These meta operators feature different hardware activation interface parameters according to various computation modes. Utilizing the architecture abstraction and the computation mode, we also implement a multi-level scheduling strategies to enhance the emphasis of DNN inference on SIM. We employ a method-level joint scheduling optimization strategies to effectively explore the scheduling space of the SIM architecture and generate the corresponding meta operator flow. Computing graph grid optimization takes the ONNX model and chip-tail hardware parameters as input, focusing on optimization tailored for core model SIM chip. In this model, we cannot change the computation progress inside the operator, so our focus lies on the computation graph level optimization. We start by employing an operator duplication strategies. As the example shows, without duplication, lots of SIM resources may be wasted. So we propose to employ a dynamic programming method to automatically determine the duplication of each operator. It can greatly reduce the latency while improve the resource utilization. Furthermore, to avoid pipeline stalls because of the imbalance between the computation and the data size, we adjust the duplication members for each node. We finally obtain the result of computation graph segmentation and operator duplication numbers. The next grid optimization is a matrix vector multiplication grid. In the BVAP grid optimization, the compiler averages the operation result from the CG graph sizing along with the chip and core-tail hardware parameters. Since the mapping granularities change from the core to crossbar, we can update the duplication of operators utilizing the idle resources to reduce the latency. In terms of computational parallelism, we introduce the crossbar granularity pipeline strategies to reduce the ping power consumption. As the example shows, The existing method will activate all the crossbars once it gets all the input, which may bring extremely high ping power consumption. Fortunately, as the example shows, through our crossbar level pipeline, we make full use of the advantage of selectively activating crossbars in advance, thus reduce the ping power consumption. The final level of optimization focuses on vector level scheduling. In the word-line model, parser rules within the crossbar can be activated at the same time, offering a more streamlined interface for vector matrix multiplication compared to crossbar model. To reduce the latency, we propose a remapping method that transforms the computation of data with accumulation relations from serial activation to parallel activation. As the example shows, in the original case, we need 4 circles to complete the whole computation. By redistributing this computation across the 4 crossbars through remapping, we enabled advanced output of the AC part, allowing operation 2 to compute sooner. Our remapping method significantly reduced the inference latency for the optimization and performance. And please refer to our paper to see more method details. And here is our evaluation result. Our hardware configuration is shown here, adhere to a commonly used setup in many works. Our benchmark include 2 different types of network. One is the conventional-based ResNet, and the other is the transformer-based reality, providing comprehensive insight to our communication sticks efficacy. For performance comparison, we employed 3 SIM chips with varying computing mode and size. Additionally, we compared our work with existing compilation framework for SIM. Compared to the same chip in various models, we have achieved 2.3 to 3.7 speed up and 75% power reduction. This finding shows the effectiveness of our method across all computation modes. Moreover, compared to the SOTA compilation stick polyhedral-based compilation, we achieved a 11% reduction in latency, which means our multi-level scheduling optimization has desired result. As the hardware resource increases and across different hardware configuration as well as computation modes, our compilation stick delivers superior performance. It aligns with our objective of building a general compilation stick. In conclusion, we designed a general SIM compilation tool through hardware and computation abstraction, a multi-level scheduling method, and meta operators. Experimental results show that SIM MLC had worse software and hardware adaptability. In the future, we hope we can support more neural network models in multi-form formats such as PyTorch 2. Thank you, and welcome to ask any questions.
I believe this is our last speaker in the session, so.
Hi, do you consider all the non-matrix operations?
Thank you for your question. So far, we didn't consider the non-matrix operations, but I think in the future we will consider it and to imply it.
Okay, but do you think like you're mapping the matrix to many arrays, and then if you consider nonlinear like all the other operations and the routing, that will completely change how the optimal mapping will be?
I think it may determined by the operations type.
Yeah, but generally you need a SIMD processor or some other near memory logic to do those things, right? And then you need to first aggregate all the matrix multiplication results into a SIMD processor, and then you involve a lot of extra routing if you do too much, like you distribute the matrix operation to many different tails.
Sorry, I didn't get it.
Yeah, sure.
Thank you.
I actually also have a question. Was the evaluation done in simulation?
Yes, it's done by simulation.
Did you consider the effects of error and wear in the hardware?
No, we didn't.
Okay, I mean,
Yeah,
it might be worth looking into. Because
yeah.
I know that some of the analog ReRAM crossbar arrays experience, I guess, do your operators include write operations?
Yes.
They do, yeah. So if you write a lot to an ReRAM array at high fidelity, you can wear down the devices. So
Okay.
it might be something interesting to consider in the future.
Okay, thank you.
And any other questions?
So thank you, very good talk. So I have a little question. In your paper, you see you designed, proposed a novel multi-scale abstraction. And my question is, why this multi-scale abstraction is beneficial? What kind of advantages does this abstraction provide? This abstraction offered when it comes to like scheduling and mapping workloads?
Thank you for your question. To ensure the generality of our compiler, we need to support different designs. Frankly, the scheduling is not enough to control all hardware, all type of hardware. So, multi-level scheduling optimization, I think, may take full advantages of available hardware resources for computing.
Okay, thank you.
Any other questions before we adjourn? No? Okay, let's thank our speakers again.
Thank you.
If you have a talk in this session, I mean, I know some of you might have flights, definitely leave if you have to take your flight, but feel free to hang around in case anyone wants to ask you questions offline. And that's it. Thanks for attending ASPLOS. I see it. And you could also consider the fact that like if you can memory for a long period of time. Yeah, so because I know there's a lot of variations. One I